So I'll begin with the scripture. And let's see here. So this is Ephesians chapter 3. I guess I'll start in verse 9. And to bring light to what is the administration of the mystery for which ages has been hidden in God, who created all things, so that the manifold wisdom of God might now be made known through the church to the rulers and authorities in heavenly places. This was in accordance with the eternal purpose which he carried out in Christ Jesus our Lord, in whom we have boldness and confidence and access through faith in him. Therefore, I ask you not to lose heart at my tribulation on your behalf, for they are your glory. This is Paul in Ephesians chapter 3. So I'll begin with a word of prayer. Heavenly Father, we thank you again for this opportunity we have to meet together and study your creation. Just pray that you'd give us understanding this day, Lord. In your name I pray, Lord Jesus. Amen. Okay, so today we're talking about coordinate change and linear transformations. So that topic in this class is a little bit simpler than, that's not good, I've forgotten how to spell coordinate. Somebody help me out. I need to spell coordinate. Grief. What's wrong with me? What's that? Is there 2 R's? 2 O's? 2 O's, okay. Coordinate. Every so often. So coordinate change for linear transformations. Now, what I'm doing today in class should be a little bit simpler than what's in the notes, because what's in the notes it has broader applicability. So I'm really just looking at coordinate change for linear transformations on Rn. And, well, I guess I might do from Rm to Rn. Let's get started here. So, reminder, definition, if beta equal to, say, V1, V2, Vn is basis for Rn, then we defined the coordinate vector of x with respect to the beta basis. Well, we didn't define it this way, but it turns out that this is equal to the inverse matrix of the basis times x, right? So just to remind you why that was true, the calculation goes like this, right? So x is equal to, let's say, I'll use c's this time. C1 V1 plus plus Cn Vn. We can rewrite that as the matrix V1, V2, Vn times the column vector C1, Cn. But that's exactly the basis matrix beta times the coordinate vector of x. So definition, if we have a basis, the coordinates of a vector with respect to that basis are literally the weights that we need to form the linear combination with respect to the basis. And so like I can rewrite that as a matrix equation and see I can solve for the coordinate vector of x with respect to the beta basis. See what I get? I get x beta is equal to beta inverse times x, right? It's just that. So that's my formula. Now, if you're reading my notes, I also use the following notation, phi sub beta of x, like that. So this phi sub beta is the coordinate map. Phi beta is a mapping from Rn to Rn, the coordinate map. That's more exciting in the 321 course because the coordinate map in the 321 course will go from an abstract vector space to column vectors there. But this coordinate map is a linear transformation on its own right. And in fact, it's a bijective linear transformation. You can easily see that that's the case, right? Like what's the matrix? What's the matrix of the coordinate map? Well, the matrix of the coordinate map is just the inverse basis matrix, right? See that? And if we sort through things, if the matrix of a linear transformation is invertible, then the linear transformation is invertible. All right? because that would, if beta is if the beta inverse is the matrix of phi beta, that means that it's an invertible matrix, so its row reduction is going to be the identity matrix. Which, going back to the last class, is going to mean that it has n pivot rows. It's going to have a null space of 0. It's going to be it's going to be an onto and one-to-one map. All right, I'll shut up. Enough about that. Question. If beta bar equals to v bar 1, v bar 2, v bar n is another basis for Rn, right? And we have x is also equal to, of course, beta bar inverse times, my bad, x beta bar is equal to beta bar inverse times x. How are, the coordinate of x with respect to the beta basis and the coordinate of x vector with respect to the beta bar basis related? So that's really my question at the moment. If we were to calculate the coordinate vector for a given vector and we wanted to compare it for different choices of basis, how would those be related? So can you figure it out? How would we relate the coordinate vector with respect to the beta basis and the coordinate vector with respect to the beta bar basis? Can you guys have any ideas?
Or x beta times beta is equal to, well, I guess that's reversed.
Oh, okay, so I like what you're going. So you're like, take the blue box, right?
Yeah.
And just rewrite that. Like this is more interesting, right? X is equal to beta, then the coordinate vector with respect to beta, right? But by the same token, it's equal to the beta bar matrix times the coordinate vector with respect to the other coordinate system. Because x is x. Like x is the vector we're describing according to two different choices of coordinates, right? So how are these related?
Whichever one you want to solve.
Yeah, exactly. So precisely. So we can solve. Let's solve for the barred one. So x beta bar is equal to the beta bar matrix inverted times the beta bar matrix times x beta. Now, in linear algebra books, in the interest of confusing the students, this is generically called P. Which is kind of obnoxious. I much prefer the notation just to be, I like this explicit notation. This is what's going on. But I think it's better if at least we can say it's the P to go from the beta system to the beta bar system, let's say. All right, at least put a notation which tells you what's going on. It's switching from the beta to the beta bar system. I think as a best practice, you should be comfortable with deriving this for yourself. Like take 3 minutes to derive it for yourself. Make sure you understand what you're doing. That way when you're doing coordinate change, you're just not blindly following some template in the book which you don't fully understand. So if you have to use it wrong, you're going to not know what you're doing. If we understand where it comes from, then we can use it more coherently. Okay, so what's the deal with linear transformation? So, and I have an explicit example to compare coordinates in different coordinate systems. I'll put up on the projector here in a bit. So we'll come back to some examples of this. But linear transformations, recall what we found. We found that if we have a linear transformation T of x, we can write it as like the standard matrix of T, right? The standard matrix of T times x. And do you guys remember how we defined that? This was what we said. This was standard matrix of T. Well, this equation pretty much defines it. But if you want another way to look at it, this is T of E1, T of E2, dot 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 t of en, right? So to find the columns in the standard matrix, we just look at what the standard, we look at what the linear transformation does to the standard basis. That tells us the columns. All right. So now I'd like to ask a question, which is, can we look at the formula for the linear transformation with respect to a different choice of basis, right? Like what should that look like? So maybe we could write this instead as a new matrix T with respect to the beta matrix, all right? And I'm actually going to do beta comma beta to be consistent with my larger program of notation. I know that seems kind of redundant, but well, if I'm sufficiently awake, I'll show you why we might do that later. I guess as a kindness to you guys, if you just write T with one beta, I'll be okay with it. I know it's like painful to write more than you actually absolutely have to, but like my Calc 1 students, they won't even give me equals between equations. I don't know. Maybe I should start every Calculus 1 with like, I hand out a bunch of those like hand crunch, like strengthener things. We just spend 5 minutes going like this, like strengthening them, because all they've done is like punch buttons on these, you know, electronic homework things for like their whole high school. I'm assuming. So guys, I'm suggesting we can write the formula. I think this is how it goes. I could be wrong about this. Oof. Oh, let's see here. So, okay, so then my question is, if this is true, so suppose this, all right? Suppose this defines that matrix. Can you tell me what the formula would be for it then? So we've got the matrix of T. We can rewrite X how? Just like we did over here. We can rewrite X as the basis matrix, right, times the coordinate vector with respect to the beta basis, right? We can rewrite X as a linear combination of the basis is what that is. This formula over here, it's just a simple formula to express the fact that we can write X as a linear combination of the beta basis. That's all it's saying. So X, right, is literally this, and that is equal to the new matrix of T times the coordinate vector X beta, right? Oh yeah, that's not true. Rats. Curses. Well, I tried. Sorry guys, this is not true. It's not true. I mean, most of the equations I just wrote were true, but that is not what that matrix means. All right, let's try that again. I mean, I could just write down the formula for you, but I really want to try to explain to you where it comes from. So T of X is equal to the matrix of T times X, right? But that's specifically the sum over I and J of the matrix of T, the, oh goodness gracious. Oh, yowzers. Well, we've got X sub I think it goes I, j, x sub I, e sub j. I mean, it's 50-50, I'm right. Either the I goes with the basis or the I goes with the coordinate. It's one or the other, okay? So like 50-50, I'm right. Just a reminder, like the matrix multiplication, if I have A times X, if I look at the ith component of that, I believe that's equal to the sum j equals, sum over j, let's just say, of A, goodness gracious, I want to say it's I, j, x, j, I think. Is that right? Sorry, I'm having a moment of doubt. Let's work it out. So how does that go? Like the first one is what? A11, x1, A1n, xn. So let's see here. So the j is summed over, and that gives me the, yeah, you're right. So did I get the pattern right? I did not. See, I told you 50-50. It's a good thing I checked, right? So you see I've got them flipped. So the sum over the coordinate is supposed to go with the second one. So I should have here, like, let's put the j on the x and put the I over here like that. So we'd like to also have that equal to like the sum over I and j of the new matrix that we're trying to define. All right, the ijth component of that times the coordinate vector of x with respect to beta. Horrible notation, guys, I'm sorry, but j. And then instead of the standard basis, we want to have the, the vi in my current notation, right? Where that's the I basis element of beta. Yeah.
Maybe I would say, why did you switch the I over j again?
Because that's how they work. Like, here's the formula for AX, as I verified over here with our explicit matrix multiplication. You see what's happening? 1, 1, and n. So it's the column index of the matrix, which is summed against the component of the vector it's multiplying. And then that gives you the ith component. But then the thing is, AX is equal to a sum over I of AXI EI. In other words, this you can rewrite as like a sum of the first thing times E1 plus the second component times E2, da 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 da. Any vector we can rewrite, like any vector generically speaking can be written as its components times the standard basis like this. So I'm just, sorry, there's got to be an easier way to get to this. I'm just trying not to use the notes, and it's actually kind of a pain. There's something I do in the notes with diagrams which makes this way easier for me conceptually. But that's a 321 thing, so I'm trying not to do it. All right, anyway, okay, so now what? So now I've got this is equal to that. I'd like to relate those, right? So what I can do is I can take my basis, right? Where was I? What is VI? VI is, check this out, if we take V1, V2, Vn, which is the basis matrix, right? What happens if you want to just get Vi? What do you do? How do you pick out the ith column of the matrix? What do you do? Multiply the matrix by what? Surely someone here remembers this. EI, right. Matrix times EI picks out column I. That is something worth remembering. So I think that's going to be the secret sauce here. So I can put that, just like you said, EI there, which means I can trade this here, right, for a sum over I and j of the matrix that we're trying to understand how to formulate at the moment. And we've got our x beta, the jth component of it. Now Vi was the basis matrix beta, right, times EI. Oh man, that's weird. This formula's weirding me out. But if I haven't made some sort of grievous mistake, we do have, see this, and that we can compare, see, because they're equal over a basis, so we can equate coefficients. Equating coefficients gives me that the sum over j of Tij xj is equal to the sum over j of this non-standard matrix T beta beta ij matrix beta j, and this is the part that's weirding me out. Oh, it's because that's beta ei. Okay, that's fine, that's fine, that's fine. And that's true for each I. You know, let me phone a friend. All right, I have tried. I've been fighting it. I mean, I think this is right, but I'm reluctant to pursue this further with you guys because it's just not. I'm about 90% sure it's okay, but I'm not confident. So let me show you the way I do it in 321. I think it's just going to be easier. I'm going to leave this. So here's the way I think about this in 321. I think it's probably, maybe it's just easier. So here's Rn. Here's Rn. I think about the linear transformation going from here to here like that. I think about this being my beta coordinate transformation. I think about this being my beta coordinate transformation. That takes me down to Rn again. That takes me down to Rn again. Up here I have the point x. Here I have the coordinate vector with respect to x beta. Where does x map to? X maps over here to, let's say, y equals to t of x. All right? If you like. Or you could just say to t of x. What does t of x map to? Well, t of x maps down here under the beta coordinate map to the coordinate of t of x. All right? The matrix I'm trying to define for the last 15 minutes, unsuccessfully, because apparently I'm an idiot, is this down here. So I want this to be left multiplication by like the t beta beta matrix. In other words, what I want is that I want t beta beta times this vector, the coordinate vector of x. I want that to give me the coordinate vector of t of x. There we go. This is the definition. Sorry, guys. This is sad. So here we go. Definition. Right there. I thought, see, yesterday I did like, I don't know, 4 hours of physics in my office hours. I don't know if you guys know this or not, but physics is hard. It apparently burnt my brain. Like, I'm still brain dead from physics yesterday, apparently. This is your brain. This is your brain on physics, something like that. Oh, I'm sorry. That commercial's from before your time. Jays know what I'm talking about? Okay. Oh, good, good. So, the drug war lives on in your hearts. That's good. Now, so much like the war on poverty, we also lost the war on drugs, as is like manifest by the, 100,000 fentanyl deaths every year or whatever it is. Or those just overdose deaths, generically speaking, something like that. Okay, so that defines the, what's the word here? The non-standard basis. Now we can find a formula from this pretty easily. So the formula would, let's get it out here. So we've got t beta beta times the coordinate vector of x with respect to the beta coordinate system is equal to, okay, so this is a vector, t of x, right? How do I find the coordinates with respect to beta? I multiply by the beta inverse matrix, right? Times tx, right? But what is that equal to? That's the standard matrix of t times x, right? But we can rewrite x in terms of the beta coordinate system. How? Remember, we had it over here. X is equal to, what is it? Beta times the x, beta times the coordinate vector of x beta. Ah, there you have it. So we're almost there. This identity here, right? This is true for all choices of your coordinate vector x beta. So the only way that can be true is if what? So we have the following, theorem. The coordinate, the matrix of t with respect to the non-standard basis beta is simply obtained by beta inverse, the inverse of the beta matrix times the standard matrix t times the basis matrix again. So there you go. That's that. So this is the coordinate change rule for a linear transformation with respect to a non-standard basis. What if you wanted to do the same thing we did at the start of class and relate two different, the matrix of a transformation with respect to two different choices of basis? Like, what would be the analog of this rule here? Right, guys? What would be the analog of this rule, but for the matrix of the transformation? What could we do? What I would do is just write down the corresponding rule for the barred basis, right? So you got beta bar inverse times matrix, the standard matrix of t times the beta bar basis, right? If this is true, then that's true. Solve them both for t. Solve them both for the standard matrix of t. What do you get? We get that. Now let's solve for the bar one. What do we get? So the matrix of t with respect to the barred basis is equal to beta bar inverse times the beta matrix, the matrix of t with respect to the beta basis, and then you got beta inverse times beta bar. In terms of that annoying p notation I introduced way back here, p was what? P beta beta bar was p beta bar inverse p beta, right? What is this here? So this is apparently p, right? What's this here? I need some space. Goodbye, wonderful diagram. You served me well. So if we have p is equal to beta bar inverse times beta, what happens when you invert that? We do socks shoes, right? The inverse of the inverse is the what? Just the matrix again, right? What's that? Hey, look, that's P inverse. So there is the theorem. If you have the matrix of a linear transformation with respect to the Bard basis, it is also equal to P times the standard matrix with respect to your beta system times P inverse, where P is related, it's what it is the beta bar inverse, I'll get it eventually here, beta bar inverse times the beta matrix. Can you guys explain to me what is the meaning of P? Like what is this thing anyway? What is beta bar inverse multiplying by beta actually equal to? Let's work that out. You've got beta bar inverse times V1. Beta bar inverse times V2. Beta bar inverse times Vn. What is that? What is it if you multiply the inverse basis matrix times a vector? What does that give you? That gives you the coordinate vector of that vector with respect to the basis. So this is exactly the coordinate vector of V1 in the beta bar system. This is the coordinate vector of V2 in the beta bar system. The coordinate vector of Vn in the beta bar system. In other words, the change of basis matrix is formed by finding the coordinate vectors of the old basis with respect to the new basis. That's what the coordinate change matrix is. So, but anyway, as a formula, we can just say it's the product of the beta bar inverse times beta. That works just fine. All right. Let's see if we can work it out an example here. Sorry, it took me longer than I wanted there. I was really not trying to spend that much class time deriving these formulas for you. Thank you. But yeah, I'm lost without my shirt. My hand's all filthy now. How do people live like that? I don't know. Let's see here. So let's work this out. Let's try to actually put this into practice for a specific example. And I have an example prepared. Well, sort of. Here it is. Example 1. Suppose we have t of x, y, z equal to, well, let me just get straight to the point. 9, 7, minus 13, 7, 9 minus 13 minus 13 minus 13, 29 times xyz, right? So if I do that, that makes this the standard matrix of T, right? I want to let beta bar, let's say, equal to U1, U2, U3. I guess I'll put bars on them. And specifically, we're going to let U1 equal to, fine, 1 over root 3 times 1, 1, 1. U2 is 1 over root 2 times 1 minus 1, 0. And U3 is 1 over root 6 times 1, 1 minus 2. This is a very nice basis. All right, very nice, very, very nice basis. Why is this so nice? It's very nice. So can you guys tell me what's the nature of this basis here?
Symmetric.
The basis is symmetric. Ooh, I don't know. Wait, so, let me look at that. Are you right? I mean, you might be right. I don't know. So, like, we've got 1 over root 3, 1 over root 3, 1 over root 3. I don't think it's symmetric. But maybe you mean something you're not saying. Like, maybe you're meaning, maybe you said symmetric, but maybe in your heart you're saying orthonormal. Is that right? Okay, good. The reason he's right in his heart, and we should all follow our heart, right? That's like from 1 Hezekiah 10:13, you know? So, which I just made up. But each of these vectors has length 1, right? Check it out. Like the sum squares of the lengths equals to 1. A third plus a third plus a third is 1. A half plus a half is 1. A sixth plus a sixth plus 4/6, 1. What else can you say? The dot product of these with any two of them is what? As long as they're distinct. Like, what's the dot product of these two? Search your heart. Find your heart is empty. There's a 0 there. Let's see here. Again, our heart is empty. 0. Even this one. 1 plus 1 is 2. And 2 minus 2 is 0. So, So this is an orthonormal basis, meaning that any two bases, they're perpendicular and all length 1. That means because of, remember this homework problem we worked out? Do you guys remember this? We had a homework problem where we proved that if you have an orthonormal set and you glue them together to make a matrix, then what happened? In that homework problem we saw that in that situation we have that beta bar times its transpose times beta bar is just equal to the identity matrix, right? So what's that mean? The transpose is the inverse, right? In other words, this is an element of what we called O3, the orthogonal matrices. I'm not sure if it's a special orthogonal. Like, is the determinant of this thing 1? Let's not find out yet. Let's not find out. Well, actually, I guess we could find out. You guys tell me. I really don't know. Is the determinant of this 1 or minus 1? Them's your choices. I haven't checked. I don't really know. All right, so let us calculate the matrix of T with respect to the basis beta. What's that? Is 1. Woohoo! So since the determinant of this one is equal to 1, in fact, beta bar is an element of what's called SO3. These are actually the rotation matrices. O3, it's got rotations and reflections. So, which are sometimes called rotor reflections for whatever reason. Okay, so let us calculate the matrix then with respect to the non-standard basis and try to understand. Let's also try to appreciate like what that means. All right, so thankfully we're just doing so we just do beta beta bar inverse, right? The standard matrix of T times beta bar again. And how does that go? That's actually the transpose, right? We just transpose it. So that's just beta bar transpose, thankfully. And so how do you transpose a matrix? Just take your column, make it into a row, right? We take our second column and make it into a row. Take our third column, make it into a row. Then I've got my T here, 9, 7, minus 13, 7, 9, minus 13, minus 13, minus 13, 29, all right? And then my beta bar matrix, which is 1 over root 3, 1 over root 2, 1 over root 6, 1 over root 3, minus 1 over root 2, 1 over root 6. The only drag with these orthogonal matrices is they're always chocked full of roots. But, you know, hey, a few square roots is a small price to pay for not having to invert a 3 by 3 matrix, right? Can we agree? Now I just need you guys to multiply these. Okay? So I'm going to need you guys to help me out here. So let's see here. We get what? 9 plus 7 minus 13 is what? 3. 3 over root 3 is root 3. How about the next one? I've got 7 minus 9 minus 2 over root 2 minus root 2. The next one, I've got minus 13 minus 13 minus 29. Wait a minute, minus 2 times 29, isn't it? Yowzers, what's that? Oh, that's not a 3. Don't let me do that, guys. That is a 6. This matters. So what do we got? When I multiply this by that, I get minus 13 minus 13. How many do I got? 58? Yeah, that feels right. So 50 minus 58 over the square root of 6. That's weirding me out a little bit. I don't like that. But, well, anyway, here we go. So when I take, whoa, dude.
It's actually minus 84.
This is minus, this works out to minus 84?
The 58 is.
Oh, minus 84?
Yes.
Oh, thank you. I feel better about that. What is that then? What is 84 over root 6? 84 is what? 6 times what? So that's actually 6 root 14. Excuse me, 14 root 6, right? With a minus. All right, so we've got what? Oh, man. Oh. It's not what I was expecting. Huh. Did I? If you guys gotta double check my steps too. If I made some kind of stupid mistake, let me know. Okay, so that apparently is what? 1. Oh, did these cancel? Like is minus, I'm sorry. So is minus root 2 over root 3 minus 14 root 6. Oh, they can't cancel. They're both negative. But that does drat. I can't see my way through it. I'm sorry, guys.
I'm a bit confused on where the column matrix came from.
Which one?
Square root of 3, negative square root of 2.
The 3 by 1 matrix.
Oh,
That is supposed to be a 3 by
good grief. What's wrong with me? Yeah, how did I do that? Oh, seriously? Good grief. Come on, guys. Somebody's got to reel me in before I get that far away from it. You're justifiably confused. So, listen. Sorry, I apparently have forgotten how to multiply matrices. That's a great sign for today. All right, so there's a ugly matrix full of roots here, and when we actually do that, what are we going to get? We will get 3, 2, and 42. That's right. Very good. Who said that? You just guessing, or? Good guess. Now, so what this means is that if we want to, we could write t of x if x is equal to, if x sub beta bar is equal to, let's say, like, you know, but yeah, that's what it is. Let me not try to say more because I don't have enough time to write everything. But we could, and the rest is 0. So it actually, with respect to this change of basis, we have gone from this ugly, complicated matrix to this wonderful diagonalized matrix, which means that if we look at the formula for the linear transformation in the beta bar system, the formula is way, way simpler, right? Like the formula in the beta bar system, if you like, you could kind of write it like this, like t bar of x bar is, well, it's just 3 x bar 1. Well, I don't want to write this because this is, I'm not going to write that. Let me not write that. But we could check this if you believe. So here's a double check on our work. What is invariant? If I want to calculate, like, for example, the determinant of the matrix with respect to the beta system would be the determinant of what? Like P standard matrix of T, P inverse, right? So that's just the determinant of the standard matrix, right? So like if you were to calculate the determinant of that matrix, you better get 6 times 42 if we're going to be consistent. Something easier to check is the trace, right? We can also show that the trace of the non-standard matrix had better be equal to the trace of the standard matrix, because again, this calculation that we've went through before, right? The trace of similar matrices is equal. Is the trace of that matrix equal to the trace of that matrix? What we got? 3 plus 2 is 5. 5 plus 42 is what? 47. What's the trace of this? What's 29 plus 9 plus 9? 47. Not an accident. So I'm sorry I couldn't multiply this matrix successfully, but if I had, and you work through it, you should get to that. Now, I'm sorry, I have somehow run out of time, but what I was going to show you guys is the example in my notes. If you look at page, come on, where'd you go? So in my notes, I have an explicit 2x2 example, example 5.4.16. In that example, I take two different choices of basis for R2, and I calculate the coordinate vector for a specific vector with respect to those two different coordinate systems. And I even draw a picture to show you how these things are related in terms of the specific geometric breakdown. So I'm going to try to take my camera home and make a little video where I walk you through those notes. It shouldn't be a long video since I've wasted your time in class today. And so sorry. Anyway, I hope your day is more successful than mine so far.